The fun of the fairground, a whirl of movement designed to thrill. He never rides a roller coaster, but Isaac Newton first describes these movements. Since the 17th century, his laws of motion are the basis of classical mechanics. We may not understand Newton's theory, but we can see that it works in the motion of the planets and the turn of the Ferris wheel. Inside the atom, where distances are tiny, things don't behave in such familiar ways. Classical mechanics no longer work. They must yield to quantum mechanics. So strange are quantum mechanics, they take years to gain acceptance. But physicists realize that not only do quantum mechanics work in the small scale, they apply to the large scale, where they're identical with Newton's predictions. In abandoning classical mechanics, nowhere is there more confusion than in understanding light. Newton's idea is that light is a stream of particles. Later, another Briton, James Clerk Maxwell, develops the idea that light is formed of waves, the distance between waves being the wavelength of that light. With red light the longest, wavelengths shorten right through to violet. They rise and fall every few thousandths of a millimeter, and they do so billions of times a second. The speed at which they ripple is their frequency. Violet has the highest frequency. So why this apparent shift from Newton's stream of particles to Maxwell's light waves? Common observation would back the particles notion. Light appears to travel in straight lines until reflected by a surface or bent by the likes of water. But this says the opposite. Light from a single source is forced through two narrow slits. The slits become light sources, light from one interfering with the other. The resulting bands, peaks and troughs of light, can only be produced by waves. It's a dilemma. Is the particles theory dead? The contradiction is resolved by a fresh approach to classical physics. It happens on three fronts. Firstly, no one can explain why objects change color as they get hotter and emit more energy. Classical physics has no answer. But one man does. He says, imagine the energy is radiated in amounts that are multiples of very small packets called quanta. The seeds of quantum theory are sown. For this novel idea, the brilliant German physicist Max Planck is awarded the Nobel Prize in Physics. Planck's theory correctly predicts the spectrum of radiation emitted by stars like the Sun, which the classical approach had failed to do. The quantum theory gains credence. Albert Einstein picks up on energy quanta. For solving a second conundrum of classical mechanics, the Swiss-born American wins the Nobel Prize in Physics. Einstein's work is with the photoelectric effect, the observation that when ultraviolet illuminates a light-sensitive metal surface, electrons are emitted. Classical physics says that if the light is intense enough, whatever the frequency of the ultraviolet, electrons will be released. Einstein says no, light intensity doesn't matter. Instead, he regards the ultraviolet as packets of energy, quanta, which we now know as photons, like the bags aimed at these coconuts. Einstein finds that the photons, the bags, must have a minimum energy to knock out an electron, a coconut. The higher the light frequency, the greater the photon's energy. In the third move towards quantum mechanics, Denmark's greatest physicist, Niels Bohr, applies the theory of Planck and Einstein to the atom. Bohr wins the Nobel Prize for Physics. Within the atom, Bohr proposes that electrons don't orbit the nucleus randomly. Instead, they're in fixed, allowed orbits, each corresponding to a fixed energy state. If incoming radiation knocks an electron into a higher energy orbit, the electron soon returns to its original orbit. In doing so, a flash of light is emitted, a photon. Bohr shows that photons are only emitted when electrons jump suddenly from higher to lower energy states. But it's still unclear. How can waves like light have photons behaving as particles? This Frenchman, Louis-Victor de Broglie, suggests a duality and wins the Nobel Prize in Physics. Every particle, predicts de Broglie, everything, including these cars, has wave-like properties. Electrons with relatively big wavelengths display such properties. These cars with minute wavelengths don't. They hide such behavior. This wave-particle duality is key to quantum mechanics. 3 years after de Broglie's prediction, this American physicist, Clinton J. Davison, and the Briton George Paget Thomson prove it. They win the Nobel Prize in Physics. They show that when a beam of electrons is fired into metal foil, they're scattered by the atoms within. The electrons are behaving like waves. It's because the wavelength of the electrons in the beam matches the spacing of the atoms in the foil. The result is an observable effect. The German, Erwin Schrödinger, takes the next step and wins the Nobel Prize in Physics. He develops an equation describing the wave properties of particles. It's complex. Back at the fairground, the total energy of a car on this ride equals its kinetic energy, that's the energy of motion, combined with its potential energy, stored energy. At the top of its trajectory, as the car teeters, it has no kinetic energy, but retains potential energy. When the car falls back, kinetic energy and momentum increase as the car gains speed. Schrödinger's equation applies this relationship of potential energy, momentum, and total energy to the motion of the single electron in a hydrogen atom. His so-called wave equation becomes the benchmark in physics for predicting the properties and behavior of particles. Next, the Briton Paul Dirac writes a new equation for the electron. It incorporates Schrödinger's theory and Einstein's special theory of relativity. Dirac, who wins the Nobel Prize in Physics, predicts that electrons can exist in two energy states. One is the electron as we know it. But what's the other? 4 years later, the American Carl David Anderson finds it, the positron, the antiparticle of the electron, the first known antimatter. He wins the Nobel Prize in Physics. In Schrödinger's wave equation, the position of electrons in an atom is only probable. The distance of their orbits from the nucleus can only be their most likely positions, because, at a given moment, there's one chance in 2,000 that an orbit will be 5 times farther from the nucleus. Such probabilities are calculated using the mathematics of quantum mechanics. The man who does it is Britain's Max Born, originally from Germany. His probability interpretation of Schrödinger's theory prompts a Nobel Prize in Physics. This is one of the most astonishing consequences of Born's interpretation. Like a man running through a solid wall and leaving no hole, particles can tunnel through energy barriers. Classical mechanics say it's impossible. Quantum mechanics say it's commonplace. Today, such tunneling is the basis of many electronic devices. Grasping that the weirdness of quantum mechanics can mess up experimental measurements, the German Karl Heisenberg wins the Nobel Prize in Physics. Heisenberg's uncertainty principle is the essence of quantum mechanics. Everyday experience no longer applies. Particles behave as waves, and waves as particles. There's no problem measuring the position and velocity of these machines, but at the atomic level there is, because our very act of measurement affects what we're measuring. In quantum mechanics, it's impossible not to jolt the tiny entities we're trying to measure.